to microbial resistance. Enterobacteriaceae, this type of bacteria, they are really resistant to antibiotics, and they're common pathogens for nosocomial infections. So the resistance is transferred from one bacterium to another bacterium using extrachromosal R factors that self-replicate inside the bacteria. So these bacteria synthesize enzyme that acetylates, phosphorylates, or do processes that can inactivate our aminoglycoside. So ito yung parang scenario ng aminoglycoside resistant property ng ating Enterobacteriaceae. Okay, so the aminoglycoside is a potent bactericidal for gram-negative bacteria. So we really have to ensure that our aminoglycoside will be upgraded in its different rings, will be upgraded to have resistance against bacterial inactivating enzyme, so that it can do its action as bactericidal for gram-negative bacilli, most especially. So, saying that, there are still points, or there are still hope that this enzyme used for overcoming aminoglycoside will be addressed, or will be overcome by the drug itself. So when we develop aminoglycoside, we need to consider the following. So absence of the target functional group, then the antibiotic will be resistant to the enzyme. So as I mentioned kanina, we will remove 3-hydroxy and 4-hydroxy so that phosphorylation of the enzyme will not occur. And then steric factors, kanina, the axial and equatorial positioning of hydroxy will allow, will confer resistance to the attack of our enzyme. And we have, just for discussion, the same with our penicillinase, we have aminoglycoside inactivating enzymes produced by our bacteria. These are the aminoacetyl transferase, phosphotransferase, and nucleotidyl transferase. So we have generally we have three enzymes that inactivates aminoglycosides. They acetylate specific parts of our aminoglycoside ring. So for aminoacetyl transferase, it acts on ring 1, and phosphotransferase, it acts on ring 1. As I've mentioned kanina, ring 1 is the major carrier of antibacterial activity, but it is also the major target of enzyme inactivation. And nucleotidyl transferase, it acts on ring 3, or sometimes in ring 1. Ayan. So these are a specific example per drug, how they overcome this enzyme, or how they overcome this inactivating component of the bacteria. So there are things that I have mentioned already in the previous slides, but an additional is for gentamicin and tobramycin. So gentamicin and tobramycin, they lack 3-hydroxyl group in the ring 1, so that it will not be inactivated by phosphotransferase. And then also gentamicin C1 is resistant to acetyltransferase because it is acetylated with 6 amino group in ring 1 in the kanamycin B ring. Now all gentamicins, they are resistant to nucleotidyl transferase because of the presence of our 4-hydroxyl group in the gentamicin. So therefore, removal of functional groups susceptible to attacking our aminoglycoside will help resist enzymatic inactivation and retain activity. One of the most significant breakthrough is the production of amicaison. Okay, so amicaison, it retains most of the intrinsic potency of kanamycin, but it is very resistant to the 3-aminoglycoside inactivating enzymes that are known, such as the aminoacetyl and the nucleotidyl enzymes. This is how the enzyme attacks. I just like to show it to you so you can figure out vividly para maging tangible siya, at least visibly ma-realize niyo does the enzyme activates the rings of our aminoglycoside. And we need to take away all those target components so that they will have no business at all with our aminoglycoside drug. So we have here the acetyl, we have the phospho, and the acetyl, the phospho, and the nucleotidyl. So yan yung mga site of action nila, how they inactivate our drug.